it looks like a mountain. So, and the line doesn't really fit it very well. So this is called underfitting, or the data has really high bias. So we say that it has high bias because it is not representing the data very well, and it's underfitting the data. So this is called high bias. Now, in a similar way, suppose you have the same distribution of data, as you can see, and you have a very complex model in which you have m1 x square, let's say m1 x raised to 5 plus m2 x raised to 4 plus m3 x cube plus and so on, and you have like a very complex model that is able to fit that is able to fit such a complex function. Because you have so many parameters, the curve that you're trying to fit to the data is essentially able to tweak itself to such a level that it fits perfectly to the whole data set, which you can see in this case, in the first case, where your the function that you're trying to fit, it has completely fit all the data points in your training data. Now, this also intuitively, if you try to look at it, it doesn't really look right, because if the next data point that I put, right, if suppose I add a data point over here and I'm trying to predict where, like what I'm trying to predict where this data point would lie, or I'm trying to predict the y for this data point, my curve would not give me the right value and it would be off because my curve is highly overfitting to the data. So this is called overfitting, which also you don't want to do. And such a scenario in which your curve is so highly overfitting that it essentially fits all the data points exactly in your training data set, it's called a high variance. It's called a high variance model. So we say that your model is having very high variance. You should, which is also not the ideal case. There should be a good balance between bias and variance of your model, which you can see in image 3, where it's not exactly fitting, but it's kind of representing the data in a way which where it is kind of fitting the distribution really well. And this is essentially what we are trying to do, not overfit or underfit. Right. So this is bias and variance, very commonly used terminologies in ML. And now we move to the optimization problem. So as we saw earlier, we have a bunch of data points everywhere, right? In our training data, we have a lot of data, and what we are trying to do is we are trying to come to an optimal set of parameters that can represent that can very well learn the function that we are trying to. So what are the optimal parameters for that? So for example, mx for mx plus c, what is the optimal m? What is the optimal c that will that will fit my data in the best possible way, such that if I replace x with any value of x, I should get a value of my y which is closest, which is very close to what I'm expecting, right? So that's the idea. We're trying to find m and c. So in order to do that, we need to know and we need to understand optimization, and this is very common through the whole machine learning literature. You will see that optimization is a part of each and every ML algorithm that we will be encountering from tomorrow onwards. So that's why I thought it is better to cover it in the first lecture itself. I'll be giving you a brief overview of optimization strategies that are used very commonly in ML. So how can you actually optimize? Like, if you have a function, if I have a function with me, what can I do in order to come to an optimal value? So essentially, you are trying to optimize over the loss function, right? You're trying to minimize the loss of your algorithm, right? So that we discussed, that we saw in this image, where what we are trying to do is make a prediction. You have an expected output, and from that you are trying to come to a minimal loss. And when can you actually come to a minimal loss? When you have a function which is concave. Now, what is a concave function? By definition, it is a function that has a single minima, global minimum, right? So there should be a global minimum of that function. So basically, something that looks like this, where uh, where you have a single global minima, you will be able, and it is a continuous function which is differentiable at all points. This you can essentially optimize over. Maybe you start at this point, right? Maybe you start at this point, and from here you calculate the gradient, you calculate the slope, and you move here. Then from here you move here. From here you move here. From here you move here. And at this point, you have reached the minima. You have reached the global minima of this particular curve. So you have optimized to the best of your ability to uh, to find the minima of, and so to find the minimal loss. And when you reach this point, the values of parameters that you have in your function m and c, for example, those are the values that you are going to stick to. So that's what you're trying to do. You're trying to minimize the loss, and to do that you need to optimize over that particular loss function that you're trying to use, right? So one thing is your function should be differentiable throughout, and it should be a concave function. Now, it could also be piecewise differentiable, in which case, which essentially just means that it could have local minimas as well. So, for example, this image that you see in the diagram, you can see that there is a local minima over here. This point is a local minima. This is the global minima. So, if you're trying to use a single optimization strategy, like you're just trying to differentiate at different points on this curve, and then take gradients and then move down the slope, you might end up into a local minima, right? So in that case, it does not guarantee. So if it is so this is a piecewise difference. So you will have to differentiate the curve with so it every time you run your optimization, it might or might not reach the global minima. So for that, you will have to run multiple iterations of your algorithm so that you avoid all the local minimas and you are able to find the global minima. So, but essentially, piecewise differentiable curves can also be optimized using the strategy that we are going to learn now, which is gradient descent, right? And for gradient descent, uh, the as we discussed earlier, uh, the function should be fully differentiable. It should be a convex function. That those are the two requirements that you have uh, in order to run a gradient descent over that curve. Because if it is not convex, then suppose if the curve is a concave curve, then you won't really get to a minima, right? Like this is where the optimization problem is a maximization problem. So where you have a global maxima but there's no minima as such. So when on this kind of a function, you can't really run a gradient descent. There's another technique, gradient ascent, and a bunch of other ways to do that. But this won't work on like descent wouldn't work on a concave function. You need a convex function. And this could also be piecewise convex. That's perfectly fine. You will have to tweak your algorithm in a way that you don't reach a local minima, and you're able to run in you finally converge into a global minima. And yeah, and then, I mean, another thing is it should be differentiable at all points, which is important because otherwise you won't know which direction to go in, right? So That is also an important thing, but there is a way to work around for that as well. But yeah, these conditions are essentially the base conditions to run a gradient descent. Um, Now moving on, what we do in gradient descent is you have a curve, right? You have a curve. You take a point. You what you essentially do is you are trying to calculate the gradient at that point. So based on whatever curve you have, x square for example, what you're doing is you're taking the first order derivative of that curve, right? If it is x square, it should be like this. Origin should be, but okay. But yeah, so you are trying to take the derivative at that given point, and then using you are going to use that gradient, which is in this case 2x, you are going to use that gradient to jump in the direction opposite to your given position, which is you're going descent. So for example, you use this gradient to move down the slope, and with the same gradient you keep on jumping further down and down the slope till you reach a point where if you differentiate you you will reach zero. So at this point it is not non-differentiable. So you have reached an inflection point. This is called an inflection point where this is where it is non-differentiable. I mean, essentially you won't reach there, but you are trying to reach as close to zero as possible when you are running a gradient descent. And another thing is that, I mean, uh, how to check like if a function is convex or not, right? So a convex function essentially at all points, the second order derivative of that function will always be positive, right? It will always, oh, it's written greater than zero, but it should be greater than or equal to zero, because um, you could always have inflection points within your function. You could have saddle points. Saddle points are basically they are not local or global minima, but essentially uh, points where, suppose look at this curve. So at this point, your the slope is essentially becoming zero. So this would be saddle point. It is not a global minima. It's not local minima. It's nothing, but it's just an inflection point, which is kind of resulting in your gradient to be zero. So these kind of points could be present in your curve, but still you could optimize in one of the directions, and you could further continue gradient descent in within the same function. I hope this is intuitively clear, and that's why it could be greater than or equal to zero and not just greater than. There's a typo there, but yeah, okay. So um, that's essentially in gradient descent. While we actually run the algorithm, we never calculate the second order derivative because it is very expensive to calculate. Like you won't really go to the second order derivative ever just to check. I mean, it doesn't even make sense to calculate the second order derivative, because the underlying assumption is that the function is convex. So you are assuming that. So there is no need to verify that after spending like so much compute over calculating the second order derivative, because while you calculate this, you are actually calculating a Hessian matrix over your input data, which is second order derivative matrix. In this case, so okay, I'll explain that in a later slide. But so that's why this essentially is not computed. This is just for the purpose of information that when how can you determine if your function is convex or not. So moving on, moving on. So if your function is a univariate function, you can that means you just have one variable. You can simply do a gradient descent over that variable. For example, if you have a sorry, what was that? Is there a message or something? Okay, okay. Yeah. So, um, continuing. Sorry, I thought someone asked a question, so I was checking the chat. But I'll continue. So, if you have a univariate function, simple x, you have to, maybe x square as we took earlier. You are trying to perform a gradient descent over this. You can simply run a first order derivative over this, and you continue your descent. Like you continue your algorithm, and you can reach the minima. Now, what if you have a multivariate function in which you have x1, x2, x3, and so on, right? You have a bunch of different variables. Now, how do you optimize over this? Now, using linear algebra, what essentially it allows you to do is you can calculate partial derivatives over each of these variables, right? So you have x x1, x2, x3. What you do is I can represent these variables as a matrix, right? As like in this case a vector x3 and so on to xn, and then I can calculate what is called a Jacobian over this. It's called, I mean, it's a term. So Jacobian is essentially just a first order derivative of this particular of your input function. So you have a bunch of inputs uh, of different variables. You calculate the first order derivative, and that becomes your and then for each of these variables you optimize separately. So you're essentially performing an individual gradient descent over each of these features, and you're trying to optimize to the minimal value. So if you have a multivariate function where you have a bunch of different variables that you need to optimize on, it's very easy. You just take partial derivatives of each of them and optimize over the complete function in a very similar fashion. Now, why I was saying that computing the second order derivative is expensive, because this itself is an expensive operation, calculating the Jacobian of a given matrix. Now, the second order derivative of this is called a Hessian, where after calculating the derivative of each of these, you calculate the second order derivative, and that too, partial derivatives for each of these is going to take it is and over millions of data points. It is a very expensive process, which is why you don't like there are some techniques which are called second order optimization techniques, which we will not go into. Which is not a part of not in the scope of this lecture, but those are very expensive and are not very commonly used in anywhere, like in machine learning techniques that are like in the industry and stuff. So it's very specific problems where you want to really study the function or do some constraint based optimization. That's where it might come into play. But in general, you are only doing first order derivatives over your data. And yeah, so this is essentially what grade like an outline of gradient descent, where you are trying to find the new point where you will go to, like, so again, this is I'm just trying to recreate the curve here, the same curve, x square curve. Let's say I am at this point, and so this is my p of n. I am trying to go to p n plus 1. How do I go there? I take p of n and I subtract my derivative, whatever derivative value I got, from which is my let's call delta f of p of n, which will give me the step that I need to take in. So I reduce that value and I get to p n plus 1, to my p n plus 1th point. And then I keep on jumping till I eventually reach here. Now there is a catch here that this this gradient, if this value happens to be very large, what could happen is um, what could essentially happen is second, you could you could come here, you could, and then you can make another jump here, and then you come here, and your next jump essentially happens like this, right? Where you miss your minima and you go to this point, and then you again come here, then you again come here, but the size of the jumps are so big that you are not able to reach minima. So that is why these steps, you have to minimize the size of these steps so that you are able to reach the minima. It doesn't happen that the curve kind of narrows at your global minima to a point that your step size is so big that you are jumping over the minima and you're never really able to converge. So you just keep on jumping from this end to this end and you're not reaching anywhere. So to do this, what we do is we add another term, which is your this n over here, which is also called as the learning rate. So this is a value much smaller than one, much smaller than one. Usually we take values like 0.001 something like that, so that the actual step, you reduce the actual gradient by a very small factor, and then you make that jump. So this time when you are doing it, so it will take very small steps, and then eventually you will reach the global minimum. That's the idea, right? Um, and yeah, that's essentially what's written in this slide. If the learning rate is too big, then the algorithm may not converge. Yeah, so um, that's how gradient descent works. So that is the importance of the learning rate. Like you might have heard it very commonly used everywhere. What's the learning rate you have to use? What learning rate to use? So this is where it is important. Why is learning rate important? So because you want to reduce the step size in a way that you are able to reach the minimum. Now finally, gradient descent. This is the rough pseudocode for writing a gradient descent. You take a starting point, you initialize at that starting point, you calculate gradient at this point, you take a scale step, and you keep on. So scale step means your learning rate optimized for that learning rate. You keep on iterating again over the same. In the you keep on iterating for the same process. You try to minimize to the point where your tolerance. So for example, you want to reach, so the tolerance is what you have set as the point where you want to stop your descent. So for example, you reached a point very close to zero, maybe 0.0001 level. Yeah, and then you stop your gradient descent process. So that's how you can cut it off. Now another thing to understand here is if this is not the local, if this curve has multiple local minimas, for example this case, and this is the global minima, right? So your starting point should you should run gradient descent multiple times. So, and you take different starting points, right? You take different starting points, and then you run the whole process and you come to the minimum. So for example, after running from this starting point, I came to this local minimum. After running from here, I came to this minimum, and finally, after all my iterations are complete, I choose I choose the point which is the least out of this. So of course this one is the least. So I deduce that this is my global minimum. So that's why it is important to run gradient descent from multiple points within with multiple starting points within the curve. Now, this process is not practical when it comes to real world problems. This is not at all practical. Oh, question: why is it called local and why is it called global? Okay, so local because within, so if you look at this curve, right? If you look at this vicinity, so this is called the local neighborhood of this point, right? Of all the points that lie within this locality of this curve, this is the minimum for all the points within this range, right? So that is why it is called the local minimum. And when you consider the whole curve, there is only one minima over here, which is the global minimum. So that is why a minima which is common to the whole curve is called global, and anything which is within the local vicinity of the curve. So that is why initially I was talking about piecewise differentiable. So that's why. So this is, if you consider this piece of the curve and you differentiate it, you will end up at the local minima,
Prashant, there is
right?
one more question.
Okay. Step size is smaller than tolerance. Not understood. Both entities are constant. Oh, so tolerance. So basically, tolerance is something where you are trying to cut off your training process. So that's why tolerance value is usually chosen in such a way that you can decide at what point you want to terminate the process of gradient descent. So step size being smaller than the tolerance is a termination condition. So for example, you have set a value of tolerance, right? And your step size, like for example, your step size is 0.001. Once your tolerance or the value of the calculated loss is, so this is a boundary condition that is defined here. So the value of your calculated loss lesser than the actual step size, then you can stop the process of gradient descent. So that's what it means. So you want to what is the termination condition of your gradient descent? This is what the termination condition would be. You reach a point where your loss function, where your calculated loss is less than your actual step size. That's when you terminate the process. So that's what it essentially means. Um, and yeah, so now I'll move on with the next part where I was saying that this approach is not at all practical, right? Why is it not practical? Your data set may have, say, 10 million data points, right? 3, 4, 5, 6, 7, the 10 million data points, for example. You have so much data with you, and now you are running gradient descent over all this data, right? You if and as I told you earlier, you don't want to stick into a local minima. So what you want to do is you want to run it multiple times with different starting points. If you do this with 10 million data points, and 10 million is also very modest estimate. Like we deal with data sets which have like 100 million data points. So it's not really effective. It's very compute expensive to train your algorithms on the complete data set. So what a generally followed technique is called stochastic gradient descent, where you are sampling data points from randomly from your entire data set, and you are only performing gradient descent over those points. And then multiple random samples are taken, and the gradient descent is performed over each of those samples, and then you eventually converge to a global minimum, like whatever, like it converges to a certain point, and then that's your optimal value of parameters that you are coming to. So that's what stochastic gradient descent means. That that although it might seem like, okay, we are missing out on a lot of data, but it roughly encapsulates the distribution of the data, and it works pretty well. In practicality, you might think that, okay, if I, out of these 10 million, if I'm just sampling 100,000, will it really work? But yeah, it does work in for considering all practical, for all practical purposes, and it's the most commonly used method. Another thing, as I told you, stochastic gradient descent, you start at different points. Now, this is, I'm talking from a very implementation perspective, uh, so that practically when you're implementing these algorithms, these are some things that need consideration. And this is one more thing that I told you, that you start from different starting points, right? So each of these runs of gradient descent are not really related to each other. So it is possible to highly parallelize this process. And for this, you can when you have models as large as, say, chat gpt and whatnot, those kind of models can be effectively, like the gradient descent process can be split on multiple GPUs, where each of these optimization processes run at the same time, and the outputs are then combined later on, which accelerates the process of training to a much, it makes it much faster essentially. So yeah, that's I think that's, we'll stop at that this point, and we'll continue with supervised machine learning from tomorrow onwards. Now that we know how optimization works, now we can go with things like regression, classification, basics of regression and classification problems from tomorrow onwards. If you have any questions, please feel free.
Hey, hi Prashant, Pawan here.
Yeah, hi.
There is one question regarding at the start of lecture. You are saying that for the data, whenever we are going to give the input like columnar data or graph data,
Mhm.
the best practice is to means remove the null values or maybe contain the duplicate values. Why it is, or it is not possible to machine learning do this itself?
Oh, okay, good question. So yeah, I mean, there are techniques in which, there are these auto training techniques, that there is a that's a whole active area of research where um, you could people are trying to use these large language models or even some reasoning algorithm, which can essentially try to curate the data by itself. Now that task is very time consuming. Like that's a very intensive task. But also, it's the whole domain is very much in a research phase. So if you tell me, if it is up to me, for example, I work in fraud detection, right? And that is a domain which is where the decisions made by my model are going to be very critical, as in the sense that it will be of a financial impact directly to the company if the model starts approving fraudulent transactions and stuff. So by adding this additional degree of prediction, where I can actually use my domain knowledge to curate that data, where I know what kind of, like how I could engineer this data to best give as an input to the model. I would try not to rely on another predictive technique that is trying to curate my data on its own, right? Maybe in the future there is a possibility that, these methods, like these language models themselves are able to deduce, like they are able to incorporate the domain knowledge within themselves, and they are able to curate this data. But at as of this moment, we have not reached that stage. So I mean, it is usually suggested that using your own knowledge, if you're able to curate the data to a point that it could effectively represent your model, it's good. And you can always see if there are techniques that are able to do that by themselves, you could always use them and compare them with what you have done. So you know that you can get some hints out of that as well. There are many things. Feature selection is one such thing where you are trying to find the top 10 best features, for example, that you could use for your model rather than using all the 100 features that you have. So that is called feature selection. Now that essentially uses other ML algorithms to find the top n features. That's a commonly used technique. But data preparation, you might want to use your own knowledge as of now at least. Does that make sense?
Thank you, Prashant.
Yeah. No worries.
Any more question? Okay. If no more questions are there, yeah, shall we conclude this today's session?
Yeah.
Yeah. Prashant, very nice information you have shared among all the participants. We have received personally on group in chat box. The session is very informative and helping for them to gain the knowledge as well as helping for their research work also. So this is the first day. So still 4 more days are there, and you will enjoy these sessions. Okay. Thank you, Prashant. Thank you very much,
Yeah.
and thank you all of
There
you.
is,
We will
yeah.
stop today's session tomorrow at sharp 9:50. We'll join.
So
Thank
just
you.
before you leave, if anyone has questions, you can always post on that group. I will reply on that. All
I
right.
think yeah, you have sent the PPT with you have shared PPTs with me. I'll
Yes.
I'll share it on group. No issue.
All right. Yeah. And if anyone has questions, they can also ask on the group. I will reply. Yeah.
Yeah, he is there in the group or FDP group. On
Yeah.
group also you can ask the question. I will permit you.
Yeah. Sounds good. All right. Thank you.
Thank you. Thank you very much.
Yeah.
Thank you.
YouTube लाईव्ह तर आहे हाफ सेशनचा आहे ना छान केलं तुम्ही ते काम माझं कालच मला ते वाटत होतं अगोदरपासून मला तर डाऊट होता तो डाऊट तसाच ग्रुपमध्ये ना हं. नाही याचे स्क्रीनशॉट घेतलेत का इव्हेंटचे ग्रुपवरच टाकायचे आपल्या एफटीपीचा ग्रुप आहे त्याच्यावर टाक
All of you, please fill the feedback link which is shared in the chat box.
अजून किती जण मीटिंगमध्ये आता तुम्ही ह्याचं चॅनल हे केलं का ह्याचं चॅनल जे आहे युट्यूबला तुम्ही आता याचेच टाकलं का नाही 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 पण ह्याचे गुगल मीटचं शेअर केलं का कॉन्टॅक्ट इंटिग्रेशन वाल्यांचं मीन्स त्याचंच नाव येते, त्याचंच नाव येते ह्याला होस्टिंग, मीटिंग होस्ट म्हणून.
आता त्याला काय करू शकतो मी, स्क्रीन शेअर केली डायरेक्ट, त्याचं त्यांचं काहीच नाही शेअर केलं मी.
GPUs where each of
चालू वाटतं अजून, बंद करते. बंद करू इथे, बंद केलं. तिथे लाईव्ह युट्यूब लाईव्हला ते आले माझी इन्फॉर्मेशन आता बोललेलं. बंद केलं मी ते.
युट्यूब लाईव्ह स्टॉप करा मला.
हां करू.